Thanks very much. 3D vision as a policy. So those of you who are in robotics and reinforcement learning will know what this means, but for those of you who don't, here's a definition. So a policy is a function, and it specifies an association between a set of states and a set of actions. Now, I think in terms of pictures, so this is a picture of a policy. It's in a high dimensional space, and there are multiple categories. These are the coloured patches I've drawn. When the current state falls within a particular category, it'll give rise to a certain action. And all the states within that region give rise to the same output. Now, a policy can be implemented in various ways, as I'll show. So one example is the cerebellum, where the current state is the activity of the input neurons, and the categories are defined by the synaptic weights of the Purkinje cells, shown in the high dimensional space by the red dots. So the Purkinje cell closest to the current input state in the 100,000 dimensional space determines the output. Here's another one, deep neural nets. They do the same. So if the current state is the activity of the penultimate layer, just about the last layer of the network, then the network stores vectors in this same dimensional space. So these red dots are in a 4096 dimensional space. And the network determines which category the current state falls in, i.e. which of the stored states it's closest to. So it's doing much the same. One more thing to say before I mention 3D vision. So the space of neural states is hierarchical, and here's an evolutionary example. So we're thinking about a predator that likes to eat green fish. So we're talking about one patch in this region, which is, I've recognized a green fish. So imagine that later on, it turns out that green fish with purple spots are poisonous. It then becomes imperative that the predator can distinguish green fish from green fish with purple spots. And it needs to add an extra dimension and divide that in two and have one region, which is green fish with purple spots, another region, which is green fish without purple spots, and do different things, have different action in those two cases. And deep neural nets are really not very good in general at doing this. They're not compositional. So 3D vision. How are we going to explain 3D vision using the tools that I've just described, i.e. that the brain stores a policy? Well, that's too long for a 10-minute talk. I'm writing a book on this to be published by MIT Press, but you're welcome to read the papers that are out already where I describe this. I'm going to talk about two quick examples. One is hierarchical representation of location. So here's a part of the space that I'm now talking about. Each point on this space is an egocentric representation. It's actually just a set of angles between the points in space. So if you're in a place where you could only see the mountains, then there's a large region. You could move quite a lot and not change the angles between the mountains. So you can move all over the place and the angles between the mountains won't change. Whereas if you now introduce some closer trees, you can still move a bit, but less so, and before you get detectable changes in the angles between points. So that defines your location more precisely. And finally, if you have a picnic table in front of you, there's the angles change as you move your head and that defines your location precisely. But what we've done is generate a stimulus defined description of location. It's not a grid-based coordinate frame like latitude and longitude. It's much more like a postal address. We've started with something coarse. It's like UK, London, Westminster, Downing Street, number 10. It's hierarchical address. And that's implemented in a paper by Alex Murray. And it's an example, as you can see, of the principle I was talking about, the hierarchical principle that we talked about with greenfish. So now we're going to do the same for shape. And this I'm using data from a paper from a long time ago, 30 years ago. And now the space is all possible shapes. So if you're looking at a shape, you could divide that into the possible shapes into convex shapes and concave shapes. You've done a very crude description of the shape. You'd have a more precise, you can add more information to your representation, and you can define the shape more precisely. You could define the bas relief shape. So it could be more stretched or more squashed. And these are all the same. So like the Parthenon, that's not the true shape of a horse, etc., but it's squashed in a way that we can recognize it. And finally, you can describe the shape, the real Euclidean shape, and you've only got one description of the relief. So we're doing exactly the same as we did for location, but now for shape. So we're still in the greenfish example. So if I had time, I'd talk about a hierarchical representation of a whole 3D scene, a bit like Mars 2.5D sketch, but I don't. So you have to ask me about it or read the papers. In summary, my take-home message is we should think more about the structure of state space. That's what's really key to understanding perception. I've given an example of location, which can be defined hierarchically in state space without using a 3D coordinate frame, and another of shape, which can be defined hierarchically in state space, again without using a 3D coordinate frame. And the brain is good at navigating state space. So that's where we should put our efforts. And thank you very much to those who've helped with this work, particularly the paper I talked about with Alex Murray. Thank you very much.